Hi everyone, my name is Eliran, and I will present a joint work with Benny Applebaum and with Arpita Patra about the round complexity of statistical MPC with optimal resilience. So let me first explain the settings. We have n parties that communicate over secure point-to-point channels, which means that they can send private messages to each other. And they also have access to a broadcast channel, which means that they can send public messages. And the parties want to securely compute a function f of their private inputs. Okay, so each party has a secret input xi, and the parties want to reveal the value of f on x1 up to xn, but no other information. So just to be more formal, we assume that there exists an adversary A that corrupts T parties. In this example, the adversary corrupts Mr. Yellow and Mr. Pink. And in information theoretic MPC, we consider a computationally unbounded adversary, which means that I'm not going to use any cryptographic assumptions here. Now, there are two types of adversaries. There is an active adversary and a passive adversary. So a passive adversary is the weaker kind of adversary. He always follows the protocol, but he tries to learn some information about the secret inputs of the honest parties. So this is the passive adversary. The active adversary is a stronger adversary that can deviate from the protocol, and in this way he can try to sabotage both the correctness of the computation and the privacy of the honest parties. And like I said, the parties want to compute the function f both correctly and privately in the presence of the adversary A. Now, the way to formalize it is to consider this ideal situation where the parties have access to this trusted party that can compute the function f for them. Okay, so here again I have an adversary that corrupts the same set of parties. So the adversary corrupts Mr. Yellow and Mr. Pink. And computation here is very easy. The parties just send their inputs to this trusted party. This trusted party computes the function f for them and returns the output to the parties. Right? So in this ideal situation, I trivially have both correctness and privacy. And what the security definition requires is that whatever happens in this in execution here can be simulated in this ideal situation. This essentially means that this protocol is as secure as this ideal situation. Now, there are two kinds of security. There is perfect security, which means that whatever happens here can be perfectly simulated here. In particular, it means that in a real execution of the protocol, the parties always get the correct output. And there is also statistical security, which allows a very small error probability. Okay, in particular, with very small error, with very small probability, it is possible that the computation here will be incorrect. Okay, and later I will explain why in some cases it is useful to consider statistical security. So anyway, for the cryptographers in the crowd, what we require is calling the full security, including guaranteed output delivery. Good. So now, given this definition, we should ask whether MPC is even possible. And it turns out that it is. So every function f can be computed with perfect security against a passive adversary that corrupts only a minority of the parties. Right? So here I have an honest majority. And every function f can also be computed with perfect security, but now against an active adversary. So this is the stronger adversary, but now he corrupts only less than a third of the parties. Right, and those are, of course, the results of Ben-Or, Gornwasser, and Wigderson, and of Chaum, Crepeau, and Damgard from '88. And in both cases, the bounds on T are optimal, so I cannot improve the resiliency here. In particular, there exists a function f that cannot be computed with perfect security, even against the passive adversary that corrupts exactly 1/2 of the parties. Okay, so the bounds here cannot be improved for general computation. And in both cases, the computational complexity is polynomial in the circuit size of the function f that we compute, and the number of rounds is linear in the multiplicative depth of the function f that we compute. Okay, so if you look at the path from root to leaf that has the most multiplication gates, the number of rounds is linear in this number of multiplication gates. So this is perfect security, but in 1989, Rabin and Ben-Or proved that if we compromise on statistical security, then we can improve the resiliency from n/3 to n/2. Okay, and this bound on T is again optimal, it cannot be improved, and the complexity and the number of rounds of this protocol is similar to the previous two protocols. Okay, so again, it is a polynomial in the circuit size of f, and the number of rounds is linear in the multiplicative depth of the function. Okay, so what it means is by downgrading security from perfect to statistical, we can upgrade the resiliency from n/3 to n/2. Okay, and this is an example of this qualitative difference between perfect security and statistical security, and in the paper we present some more examples of this difference. So, but anyway, as you can see, when studying MPC, there are several complexity measures that we can try to optimize. Right, we have the computational complexity, the communication, and the number of rounds. And in this paper, we studied the number of rounds of general MPC. So we ask, what is the optimal round complexity of information theoretic MPC? And I want to emphasize that this is a natural question, but studying the round complexity of MPC actually gives us a better understanding of the nature of MPC, and I will give an example soon. Good. So let me tell you what is known about the round complexity of information theoretic MPC. So for perfect security, against the passive adversary that corrupts a minority of the parties, we know that 2 rounds are sufficient. Every function can be computed in only 2 rounds. So this is the work of Applebaum, Brakersky, and Sabari, and of Gargisha and Srinivasan. Okay, and this bound is optimal. It is not hard to prove that there exists a function that cannot be computed in only 1 round. Now, for perfect security against an active adversary that corrupts less than 1/3 of the parties, in a previous work with Benny and with Arpita, we proved that every function can be computed in 4 rounds, and this bound is also tight. Okay, there exists a function that cannot be computed in less than 4 rounds. And finally, for statistical security against an active adversary that corrupts a minority of the parties, that we do not know what the correct answer is. So in a previous work with Benny and Arpita, we proved that 4 rounds are required. There exists a function that cannot be computed in less than 4 rounds, but the best upper bound that we have is 7 rounds. Okay, so there is still a gap between the best upper bound that we have and the best lower bound that we have. Okay, so this is the main open question in the round complexity of information theoretic MPC. And in fact, in this regime, we do not understand even simple primitives, such as verifiable secret sharing and single input functionalities. I will talk about them soon. And it is known that those primitives are necessary for the construction of general MPC. So if we want to understand the round complexity of general MPC, we first must understand the round complexity of these simple primitives. And in this work, we give a full characterization of the round complexity of statistical MPC with active security and optimal resiliency. And along the way, we also provide tight bounds for these simple primitives. Okay, so I will start by discussing verifiable secret sharing. So at a high level, verifiable secret sharing can be seen as secure storage. So we have the dinner here that has a secret S, and the dinner wants to store the secret S among the parties here, which we think of as secure writing. So the parties execute this protocol where everyone can send message to everyone else. And at the end of the protocol, the parties have shares of the secret S. And the main requirement here is that the adversary has no information about the secret S. So this is similar to secret sharing. And then in the reading phase, all the parties provide their shares, or maybe they execute some protocol, and in this way they can recover the secret S. Okay, so just to be more formal, if the dealer is honest, then the requirements from verifiable secret sharing are essentially the same requirements as from robust secret sharing. Okay, so if the dealer is honest, we require that in the writing phase, the adversary has no information about the secret S. Okay, so these parties that are corrupted by the adversary have no information about the secret S. But then in the reading phase, the secret S will be reconstructed, even though these parties are actively corrupt and might provide, for example, incorrect shares. Okay, so like I said, for an honest dealer, we have the same requirements as for a robust secret sharing. However, verifiable secret sharing provides also some guarantees for the case where the dealer is corrupt. So if the dealer is corrupt, it does not necessarily have a secret S, but nevertheless, at the end of the writing phase, we require that there exists some secret S that is defined by the shares of the parties here, so that this secret S will always be reconstructed in the reading phase. So whatever these parties try to do in the reading phase, the secret S will still be reconstructed in this reading phase. Okay, so verifiable secret sharing is stronger than robust secret sharing because it provides some guarantees even for the case of a corrupt dealer. Good, so this is verifiable secret sharing, this is the definition. And verifiable secret sharing is a basic primitive in information theoretic MPC because it consists only of secure storage. Right? There is no computation, we do not manipulate the secret S. And you can formalize this intuition and prove that verifiable secret sharing is actually necessary for the construction of information theoretic MPC. So, and this appears in the previous work again with Ben and Arpita, in which we prove that there exists a function f. This is a simple and explicit function, so that if you give me any protocol that securely computes the function f, let's say that the protocol computes the function f in R rounds, then the first R-1 rounds of the protocol is a VSS protocol. Okay, so this shows that VSS is necessary for the construction of general MPC. It also shows that if we want to understand the round complexity of general computation, we first must understand the round complexity of VSS. And this is an example where the study of the round complexity of MPC provides us with a better understanding of the nature of MPC. Right? We show here that VSS is not just a useful building block for a general MPC, but it is actually necessary for the construction of MPC. So let me tell you what is known about verifiable secret sharing in the settings of Rabin and Bangalore, where we require only statistical security and we have an honest majority. So there is the work of Kumar-san, Patra, and Rangan that provides a VSS protocol with 3 rounds of writing and 2 rounds of reading. And before we said that every function can be computed in 7 rounds, and therefore there also exists a protocol for VSS that requires 7 rounds of writing, but now only 1 round of reading. And it is known that 3 rounds of writing are necessary. And of course, 1 round of reading is necessary. And therefore, the main open question is, can we achieve both? Can we have both a protocol that achieves both 3 rounds of writing and 1 round of reading? And in addition, in order to use this VSS to construct a general MPC, we also want it to be MPC friendly. And MPC friendly means that if we shared 2 secrets, S and S prime, and now we want to have a share of the sum of these 2 secrets, then we can locally manipulate the shares of S and S prime in order to obtain a share of the sum. Okay, and the VSS scheme that is MPC friendly is very important if you want to use this VSS to construct MPC. But now it is known that the protocol of KPR is not MPC friendly. However, the protocol with the 7 rounds of writing is MPC friendly. Okay, in our work, we show that there exists a protocol that requires that has 3 rounds of writing, 1 round of reading, and it is MPC friendly. Okay, so we achieve all of them at the same time. Okay, so like I said, we provide the first round optimal VSS that provides statistical active security and the optimal resilience. However, there is a caveat here, and the caveat is that the running time of our protocol has exponential dependency on the number of parties, which means that our protocol is only efficient when the number of parties is logarithmic in the security parameter. Now, I do want to mention that our results are still meaningful even for large values of n, because the adversary is unbounded. Okay, so another way to think of our results where when n is large is as a feasibility result. Okay, we show that it is possible to execute VSS in 3 rounds of fighting and 1 round of reading from an information theoretic perspective. And I should mention that the question of efficient VSS is open even with multi-round reading. Okay, so for example, the protocol of KPR that has 3 rounds of writing but 2 rounds of reading also has this exponential dependency on the number of parties. Okay, so the problem seems to be with the 3 rounds of writing, we do not know how to achieve a VSS protocol that has 3 rounds of writing, and it is efficient regardless of the number of rounds of the reading phase. So those are the results regarding VSS, and let's move on to single input functionalities. And so single input functionalities are functionalities that take inputs only from a single party, and then they provide the outputs to the rest of the parties. And they capture a large class of interesting problems. It is not hard to see that zero knowledge proofs can be captured by single input functionalities. Secure multicast, where the dealer wants to send the message only to a subset of the parties, is also captured by single input functionalities, and there are many more examples. However, the best known protocol for single input functionalities requires 7 rounds of communication. Okay, in fact, the best protocol that we have here is the protocol for general MPC. Okay, and in this work, we provide the first round optimal single input functionality protocol with statistical active security and optimal resiliency. So our protocol requires only 3 rounds of computation, and this bound is tight. Okay, we can show that there exists a single input functionality that requires 3 rounds. Now, the running time of our protocol is again this exponential dependency on the number of parties, and it also has a polynomial dependency on the circuit size of the function f that we compute. And let's consider as an application, let's consider the case where we have 1 prover and we have 2 verifiers. Okay, where at most one of these 3 parties is corrupt. Okay, so we have an honest majority. And let's say that the prover wants to convince the verifiers that he knows an assignment X that satisfies some circuit F, but he wants to do so without revealing any information about this assignment X. And our results show that there exists a 3-round protocol for this 1 prover 2 verifier scenario that is efficient. It runs in polynomial time in the circuit size of the function f. It provides statistical UC security. Okay, so first of all, it provides statistical security, which means that even if the prover is corrupt and unbounded, it cannot cheat the verifiers. And even if a single verifier is corrupt and unbounded, it cannot violate the zero knowledge property. And in addition, it provides UC security, which is a strong notion of security that includes a straight line, that in particular implies that we have straight line black box simulation and knowledge extraction. And if we compare it to the standard settings of zero knowledge, where we have 1 prover and 1 verifier, then in the standard settings, we know that 3-round zero knowledge proofs require non-black box simulation. Okay, and this means that by adding just a single verifier to the standard settings of zero knowledge, then first of all, we can upgrade the security from computational to statistical, but in addition, we can obtain a UC security that implies straight-line black box simulation. So this is an application of our single input functionalities. And finally, for a general MPC, we provide the first round optimal statistical MPC protocol that has active security and optimal resiliency. So our protocol has 4 rounds of computation. And we know that this is tight. And the running time of our protocol, again, has this exponential dependency on the number of parties. It has polynomial dependency on the circuit size of the function f that we compute, but it also has exponential dependency on the depth of the circuit that we compute. But I do want to mention that this exponential dependency on the depth actually occurs in every protocol that provides information theoretic security and has a constant number of rounds. Okay, so this is a great open problem on how we can get rid of this exponential dependency. And let me just mention that we get this protocol by providing a statistical compiler. And our compiler transforms any protocol that has 2 rounds and is secure against the passive adversary into a protocol that has only 4 rounds and it is now secure against an active adversary. Okay, and our protocol preserves statistical security. And the main building block that we use here is a strong version of single input functionalities that we construct in the paper. And finally, this compiler can be seen as a variant of the GMW compiler, where we replace the cryptographic machinery in the GMW compiler with the statistical protocols for single input functionalities. And in addition, our protocol is round efficient, right? It incurs a small overhead in the round complexity. Okay, so just to sum up, we showed that the round complexity of statistical security against an active adversary that corrupts a minority of the parties is 4 rounds, and we know that this is optimal. Okay, so thank you very much.